Good morning, my YouTube viewers. It is Crystal here. I'm here this morning because I want to give you another code review. You notice if you watch my videos on a regular basis, you will notice that yesterday I gave you a code review on Flax using Boston house prices, and we did that with Flax. And what I'm going to do this morning is I'm going to give you a code review on Flax with the California house prices. And the reason why I'm using two different house price data sets is because I had to use a different optimizer on Flax for the California house prices that I did with Boston house prices. And that is one of the reasons why it's important to learn about neural networks and the different attributes of the neural networks that make them work, because on Boston house prices, we use an optimizer of SGD, that's stochastic gradient descent, and then on California house prices, we had to use Atom. It didn't work on SGD with California house prices, and I studied the code and tried various methodologies to get it work. And finally, after a day or two of studying the code, I figured out that maybe if I used a different optimizer, the program might work. So that's what I did, and that's why I am making this video, just to show you that you have to use different optimizers for different types of data sets. And you'll notice both data sets are house price data sets, but SGD didn't work on California house prices, and so I had to use Atom. And Atom is always a good optimizer to start with. There are other, an RMS prompt works pretty good as well. But that's why whenever you're working on a program, you look at different optimizers. And so if you come over here to the website for Optex, which is what we use, it gives you a listing of all the common optimizers. And so if you feel so inclined, you can try out every optimizer and see how it works. But I just used Atom. So what we'll do is we will get on with the code review. So the first thing we did was we created this program in Google Colab, and we're using the California house price dataset, which actually is loaded in Google Colab already. And then the first thing that we did when we created the program, the Jupyter Notebook, is we imported the libraries that we would need. So we imported Jax, which provides your deep learning functionality and actually performs numeric computations. We imported pandas, which takes the CSV file and converts it into a data frame, and it also processes the data. We imported NumPy, which creates NumPy arrays and performs numerical computations. We imported SciPy, which we use to get rid of outliers. We imported typing, which sets up the sequence in the tuples, and this is the first time that I've used the typing library. It's actually a module in Python, so I haven't used it a lot, but it gives you sequence and tuple, which is what we're going to use. We imported Flax, which is going to create your neural network. We imported Optex, which gives you your gradient processing and optimization. We imported sklearn to give you machine learning functionality. We imported Seaborn to statistically visualize the data, and then we imported Matplotlib where we visualize the data as well. And so you see we have a lot of libraries that we need to import to carry out this program. And then after we've imported the binaries, then what we're going to do is we're going to use Jax to set the seed. So seed equals jax.random.prng key 42. And so that sets the seed. And then what we're going to do after that is we're going to load the data set. And as I said, the data set is already in the Google program. So all you do is you load it in from Google. And so we load in the train set and the test set. But we concat the train test and the test set to make it all one set. We reset the index. We drop the index. You don't need the index. And the reason why is because Pandas automatically indexes every row of data. And so you can see this is the data frame that we have created. We're going to remove the outliers by using SciPy. df equals df square brackets np.abs z-score df is less than or equal to 3 dot all axis equals 1. So that means that I think it's if the standard deviation is greater than 3 or greater, then it will just remove those rows from the data set. So you'll see now we only have 19,128 rows. So, and then originally it had 20,000 rows. So it was like 772 rows it removed, I believe. I'm doing that I just did that in my head. I didn't use a calculator. So I hope it's 772, or is it 800? 872. And so I've done that in my head. So hope I got it correct. And then we're going to define the dependent and independent variables. Y is we're going to pop medium house value out of the data frame. And then X is going to be everything else. And then what we're going to do is we're going to create a map using Matplotlib. So this is a map of the California house prices using the latitude and the longitude. So that looks really neat, and that's some of the things that you can do with Python. Now we're going to create some scatter plots. Scatter plot is going to be the median income based on the medium house value. We're going to have another scatter plot, which is going to be total rooms, but on the medium house value. Then we're going to do a scatter plot on total bedrooms on medium house value. And then we're going to do a box plot on the age versus the median house value. So that tells you what the age of the house is and how it corresponds with the median house value. So now what we're going to do is we're going to analyze the target. We're going to use Seaborn to do that. And you can see we've got our target, and you can see we've got quite a few houses that are $500,000. So that's going to give you some outliers. And then now what we do is we do the value counts. So you can see all the value counts of each value and how many you have of that value. So you have 645 examples that are 500,001, and then it goes on down the list until you have only one. We're going to define the X variable, which we didn't do that because we did that previously. So I'll just delete that. We don't need that. Samples features equals x dot shape, and then we print samples features. So 19,128 by 8 columns. And now we're going to convert the X and Y variables to Jax arrays. And the reason why is because these arrays will not work on the Flax model if you do not first convert it to a Jax array. And then what we do is we're going to standardize the X variable, and when you standardize the X variable, you set it up so you have a mean of 0 and a variation of 1. I think that's what they call it, a variation. A mean of 0 and a variation of 1. And then so we standardized our X variable. And now what we're going to do is we're going to use sklearn train test split model to split the X and Y variables into training and testing data sets. So now we get to the point where we create our MLP. It's actually an MLP regressor. We create our MLP regressor in Flax. So you can say class multi-layer perceptron regressor, and it accepts linen.module. So linen is what create is the module in Flax that is the neural network. So features.sequence in equals 5, 10, 15, 1. And so in that one, you're using like the typing model. I haven't used the typing module a lot, so I don't know a lot about it, but it sets it up as integers. So the integers are going to be 5, 10, 15, and 1. And these are actually going to be your weights and your biases. And then you set up the function within the class as setup. So self.layers equals square brackets linen.dense brackets feet for feet and self.features. And then we create another function called call. Def call accepts self and inputs. X equals inputs for I, layer in enumerate self.layers. X equals layer X if I is not equal to len bracket self.layers brackets minus 1. X equals linen.read glue, and then you're going to return X. And read glue is an activation function, so that's what it's using. And now we say model equals multi-layer perceptron regressor. Params equals model.init seed, x train 5. So that means that you initialize the params, that's your variable params. You initialize it with the seed, and you're going to use the first 5 rows of X train. And then so for layer params and params items, print layer name, format layer params 0, and then you print off your weights and your biases, which are a tuple, and then that's what you get. You get a layer name, layer 0 equals layer weights 8, 5. So 8 is the number of features in the data frame, and 5 is the first number, right, that was declared in the previous function. And then biases is 5. And then layers 1 is, the next one is going to be the number of 5, which is the number in the previous function that had been declared under sequences, and then 10. And then, so your bias is going to be 10. Layer 2 is going to be weights is 10, 15. Bias is 15. And layer 3 is going to be 15, 1. Bias is 1. And then next thing we're going to do is we're going to make a prediction on X train on the first 5 rows of data in X train. So you can see that preds equals model.apply params, X train square brackets colon 5 square brackets. And then so you can see that's the number that you get when you make prediction or apply the X train. So now what we're going to do is we're going to set up another function. We're going to call it def mean squared error loss, weights, input data, comma actual. That's what it accepts. Preds equals model dot apply, weights, comma input data, then return J and P power actual minus preds dot squeeze, comma 2 me. Now that is to set up the model. And then the next thing that we're going to do is we're going to train the model. So we're going to set it up for epochs is 5,000. Model equals multi-layer perceptron regressor. Random array, that's we're going to define a random array using Jax random dot normal. The key is the seed and the shape is 5 and features. So you're going to have 5 rows by the number of features, which is 8. Params equals model dot init. That's initialize seed comma random array. So that's going to be your params. Now what we do is we set up the optimizer. Optimizer equals optext.atom, and that's what I had to use. If you watched my previous video had an optimizer of stochastic gradient descent. Well, that did not work on this data set, and I worked for a day or two trying to figure out what the problem was. And because I'm just here on my own doing all this stuff, I don't have anybody to help me, so I have to figure it out myself. And so I figured out myself that the optimizer was the problem. And we set it up for a learning rate of 0.01. And then next time, so what we're going to do is going to take that out because that's not SGD. And then the optimizer state is optimizer.init params. We have to initialize the optimizer. Loss grad equals jax.value and grad mean squared error loss. And so value and grad is a function in Jax. So Jax and Flax work hand in hand in this when you're making Flax neural networks. They work hand in hand. And that's why you have to install Jax as well as Flax, because Flax uses a lot of Jax functions, and that's why Flax has been written on top of Jax. And so now after we set up the variables, we're going to get into the actual training. So for I in range, brackets 1, comma epochs plus 1, loss val, comma gradients equals loss grad, params X train, Y train. So that calculates the loss and gradients. RMSC is JMP dot square root loss val, because your loss val is your MSC, but I prefer working with RMSC. That's what I'm used to. That's what I like. That's what I do. Updates, optimizer state equals optimizer dot update, gradients, optimizer state, params equals optext apply updates, params updates, and then if I divided by 100 equals 0, then you print the number of epochs and the RMSC. And you can see here it has a pretty high RMSC, which is different from the program that we had yesterday when we used Boston house prices. Boston house prices had a low RMSC, but we have a high RMSC with California house prices. So now what we're going to do is we're going to make predictions. So we made predictions on the test set. So that just tells you what you got when we predicted on the test set. And now we've got test preds. Sorry, that was the train set. This right here was your train set. We made predictions on the train set. And this is the predictions that you got when you predicted on the train set. And now we made predictions on the test set. And these are the predictions that you got on the test set. So now what we do is we're going to evaluate the model. The first thing that we're going to check is your R-squared score. And what that checks is the deviation that R-squared score. It says coefficient of determination. In statistics, the coefficient of determination noted R-squared and pronounced R-squared is proportion of the, let's check this one. It's a statistical measure that represents the proportion of the variance for a dependent variable that's explained by an independent variable in a regression.